Okay, let's get started. Today is the midterm review, as you all know. Um, so I have some PowerPoint slides for today, and I will post these after class today on the website. Um, before we get into that, any questions on homework 3, which will be all that material will be on the exam? Oh, okay. I heard that it's easier than homework 1, so I guess that's good. I thought it would be harder, but apparently it's easier, so that's good news, at least from a few people. So you should be really proud of where you are in this class. We've learned a lot of machine learning already, and we've learned all the fundamentals. And you are now know enough to do a bunch and probably most of the applications of machine learning out there. Like medical diagnostics, the input's your data, the output is the diagnosis. You know how to do that. Stock market trading, not so much. We'll get there. Virtual personal assistant, no. Self-driving cars, no. I should have gone the other way in the circle. Traffic prediction, yes. We know how to predict whether it's going to be good traffic or bad traffic. Speech recognition, build a predictive model. Input is audio, output is predicted speech. Image recognition, input is an image, output is the prediction for the image, etc. So we're able to do, of course, email spam filtering. That's your homework. So we definitely know how to do that. We know a lot of powerful real world applications from what we've learned so far, and it affects all parts of our lives. So machine learning is not just some abstract computer science thing that you learn, but it's something that's in every product that you use, and increasingly so used in of all the big tech companies like Amazon, used in healthcare, used in delivery drones eventually. People are working on some of this picture is not sci-fi, but it's in progress. So it'll be there soon. In the cloud, personal assistants, finance, banking. Eventually there'll be self-driving airplanes. I don't know if you'd get in that, but it's going to be there. And looking through the Wikipedia pages of the machine learning models, the specific machine learning models we've learned, it's just interesting to see the applications that they list there. So for logistic regression, for example, the trauma and injury severity score, which is widely used to predict mortality in injured patients, was it originally developed using logistic regression. So that's a cool real world health related application. Predict the risk of developing a given disease, diabetes, coronary heart disease, based on characteristics of the patient. So inputs, the X variables. But outside of health, this is a kind of a, predicting how people will vote. In economics, used to predict the likelihood of a person ending up in the labor force. Whole bunch of other things. And these are real world applications of logistic regression, and just a tiny subset of those real world applications. So you can do all these things knowing what you know now. Same with linear regression. Here, there's some applications in epidemiology. It looks like early evidence relating tobacco smoking to mortality was originally done using linear regression analysis. So, and that's how people learned that tobacco is bad for you. In finance, it's used for things that I don't quite understand. Fixed investment spending, predict consumption spending. I don't know what that means, but apparently it's useful for economics and environmental science. Analyses on fish to measure the effects of pulp mill or metal mine effluent on the aquatic ecosystem. And I don't really know, but that sounds important. So how biospheres are affected by pollution. So really important problems, and you know how to do this. K nearest neighbor. So for the rest, I won't show Wikipedia, but just if you search on Google Scholar, and I just chose the top appearing papers that are application oriented, you see that all these other algorithms are used in many ways. So k-nearest neighbors, forestry applications, predicting economic events, breast cancer diagnosis, structural health monitoring, forecasting, load forecasting, remote sensing, image classification, financial distress prediction. That's just a small subset of what appeared on the first couple of pages, but k-nearest neighbors is used in a lot. Naive Bayes, of course, spam classification, but text classification in general, predicting Alzheimer's disease from genome data. That's a cool application. Energy prediction, more text classification. It seems to be used a lot in NLP. Credit scoring and e-lending, treatment decisions, software defect prediction. You see, machine learning really is in all these fields: decision trees, meteorological applications, bioinformatics, stock trading, NLP, part of speech tagging, healthcare, identity verification, etc. Same, and I there's more on the slides, but you get the idea. These are every model that we've learned in class is used in basically every field. So you should feel proud of yourself that you can understand all these research papers are out there. You can go and build these models and apply them to whatever you want. So this is I think a great midpoint part of the class. And I also want to highlight some example machine learning papers, application heavy papers. I just kind of chose these at random. I'd never read them before yesterday, but just to highlight that you kind of know all the methods that go on in these papers. So here's just one random paper: machine learning analysis of high-grade ovarian cancer proteomic data set reveals novel candidate biomarkers. So if you look at the first figure of this paper, whereas before this class, you might not have known what they're doing, but now it's pretty clear. They got a data set, they do feature selection, which we're just about to learn about. They then put it into a decision tree, and they get explainable DSS, which is a term they made up that stands for Diagnostic Support System. If you go into the methods, there's a paragraph on feature selection. How do they choose what good inputs to put into the model? Then a paragraph describing their decision tree. You know all about decision trees from this class. They talk about their performance evaluation. You should see accuracy, precision, sensitivity, specificity, F1 score, all things that we've talked about. And they show a picture of their decision tree that was learned. These are gene names, and it's saying if the value of a gene name is greater than or less than a certain value, you predict tumor or not tumor as you look at different genes. And they show a confusion matrix. This is just a tabular form of a confusion matrix, but evaluating how their decision tree does. That's basically the whole paper. So this is just, the first paper I chose, basically. I didn't handpick this, but applied machine learning paper where everything, all the steps that they did, you understand it. And hopefully when you create your own project, in this class, you'll follow similar steps. Yes, question? Feature selection is not in the midterm. So the question was, is feature selection on the midterm? The midterm goes up to the beginning of clustering, so k-nearest neighbors, and it stops there. So basically all the fundamental learning algorithms and the basic machine learning process plus k-means clustering. Yes? May not be relevant, so why is it confusing? So it's in binary. So the question is, why is this called a confusion matrix? So it basically tells you when the model was confused, which is kind of not helpful. The name comes from multi-class classification, where here, let me see if I can turn off my background on Zoom. Okay, I'm gonna stop sharing really quick and turn off my background. Oops, not blur. Video, choose video filter, none. Where is it? Oh, thank you. Okay. So in multi-class classification, let's say you're predicting between 4 classes. And this might be class 1, class 2, class 3, class 4, 1, 2, 3, 4, actual predicted. It's good when you predict in here. And if you have a high number here, for example, this tells you that the true class of 4 was commonly confused to be 1. Or this cell will tell you that class 2 was commonly confused to be class 3. So that's why it's called a confusion matrix.
You mean confused with class 3?
Confused to be class 3.
What do you say? Not with. Because isn't the machine confusing the two outputs? The correct one and an incorrect one?
Now I'm confused. It's confusing the class to be. So like if there's a true value and a predicted value. And if it gets it wrong, it tells you which types of classes it tended to predict it wrong as. So for example, if you're doing, in my case, emotion classification, which I've done a lot, you take an image and you predict happy, sad, surprise, neutral, fear, disgust. In that case, fear is often confused for disgust. So it's anger. And so fear is often confused to be anger by the classifier. And you can see that in a confusion matrix. Is that clear, people? Okay. And maybe we can go back to the board for future things today. Play from current slide. So pretty cool stuff. Just one more example paper. And we'll get to midterm specific topics. So this is just another random one, but early warning system, accurate mortality risk prediction for COVID-19. So a very timely paper in Nature Communications. And here they show their study design, which is not a decision tree, it's a flow chart tree where they show, okay, we develop our model, we validate the model. Within model development, we basically find people to put in the training set. And so I just want to show you every figure to show you can understand every figure. This figure is not specific to machine learning. It's just showing how they created their training and test set, who they put in their training set, who they put in their test set. Very important decision. And then they built a model and they did feature selection by lasso. And remember that lasso, aka L1 regularization, they were able to figure out which of the inputs to the model were most predictive towards having a high risk or low risk of, I think, death or mortality from people who have COVID. And they could see here that you could get the predictive factors most in the direction towards high risk of mortality, and the predictive questions in the highest risk of low mortality. And how do they get those? Well, they look at the coefficients of each of the inputs to the regression model. So the weight, or the M of the MX plus B, tells you how strongly that input variable contributes to the diagnosis. You already know this. Yes.
What does consciousness mean?
I don't know. I don't know what they mean by consciousness here. I just chose a random paper. But the high level idea of what they're doing is that they put these curves, sensitivity over versus 1 minus specificity, and they compare these curves for different models. So they, this should look familiar as a AUROC curve for different models on different data sets. And they compare a bunch of different models, support vector machines, decision tree, logistic regression, and neural network on different data sets, and compute the accuracy, sensitivity, specificity, positive predictive value, negative predictive value, all metrics that we learned about. So Cool. You know how to do, you know how to all the knowledge needed to create some really powerful studies from what you've learned in this class. And again, I could have, at one point I wanted to do like 10 different examples just to show you you really understand the basics of machine learning now. But I know you want to be able to study for the exam. So let's start covering that. So what to know for this exam? You should know the high level machine learning process. So splitting up your data into a training, validation, and testing set. How do you evaluate the test set? So just the general framework for machine learning, regardless of what machine learning model you use, just what's the general setup for supervised learning specifically, which is about 80% of machine learning. Understand the high level of how the fundamental machine learning models work. So all the machine learning models that we covered in class, just at a high level, not at a very mathematical level. And we'll have example questions today, so you'll see what I mean by that. A comparison of these different models. So why would you use one model versus the other based on how they work? And these aren't necessarily things you can memorize. They're things that you have to understand the model to think about why you would use one or the other. But if you understand how the model works, it's relatively clear. And how models learn, which is gradient descent. And that's specifically how parametric models learn. So linear and logistic regression specifically. With respect to the machine learning process, I've found just a bunch of pictures on Google Images that describe the machine learning workflow. So we can see it in different ways. Retrieve the data, clean the data, transform the data, develop your model, evaluate your model, put it in production. It's pretty clear. Here's another way of looking at it, but looking at a different slice of what you're doing. So you get your data from databases, you clean it, you use it as training data, you represent it in some way as a feature. You train your ML model, which makes predictions from input data. So another way of looking at it, or another important way of looking at the ML process, you get your data, you train the model, you optimize the hyperparameters like you did in homework 2. For example, these are 3 hyperparameters you might optimize for a decision tree or a random forest. You train the model and you test it. And remember, you have your data set, you can split it into a training and testing, or you can split it into a training, validation, and testing, where validation is specifically for hyperparameter optimization. And this is showing that cross-validation hyperparameter optimization workflow. This is not specifically for the exam, but just a broader workflow of machine learning in the real world, because I assume a lot of you want to do machine learning in a job after you graduate. And all these steps are part of the job, but there's a little bit more to it, which is kind of hard to test in a class. But you also spend a lot of time cleaning your data. So you don't just import the data like you do in this class. You have to convert the data that's collected in the real world, put it in a nice numerical format. That's usually a lot of the work in the real world is doing that, just in general, but including in machine learning. Once you do that, do the process, train and test. Once you test the model and it works well, you package the model, make it easily callable in an application. And once it's in that application, you want to monitor the progress of the model, update the model accordingly, and use all your software engineering, if you've taken the software engineering classes, all those skills, but to the machine learning model monitoring process. Okay, so getting a little deeper into the specifics of the exam. So a little of this is comparing the fundamental ML models. And here's a figure actually from a paper that I was involved in a while ago that's just comparing several different models, those are the rows, for the same data set and performing, these are different properties of the data set, but at the end showing the sensitivity, specificity, and accuracy for decision tree, SVM, logistic regression, different types of SVMs, different types of logistic regression models with different numbers of features. And I guess the reason I'm showing this to you is that it's often hard to know in advance which model will work the best. And really, it's going to be heavily dependent on your data set. So you'll have to study your data set and understand, okay, are the data separated linearly? Apparently, is it a big data set? What's the complexity of the features, etc.? A lot of these types of questions will let you know, as well as how fast is the model going to learn given the data? How fast is it to predict? Am I going to spend most of my time training the model? Am I going to use it frequently for prediction, or is it only going to make a few predictions or one prediction? That's why, the speed of the model might be important. Here I put in a little table. Actually, I put in a few of these tables for you, and I'll post these slides. I know it's kind of hard to read. On just where other people have compared these models and given the pros and cons. So it's a little hard to read, so I'll read it for you and let me know if you have any questions after each one. So let's start with k-means clustering. So that's actually the only clustering model you need to know. But an advantage is it's very efficient and it can work with large data sets. Disadvantage is that it doesn't do well with noisy data. It's not applicable for categorical data necessarily. And it's only applicable when a mean is defined. So anyways, that's let's move on to the supervised one. So k nearest neighbors advantages are that it's non-parametric. So there's no thetas that are being learned in k nearest neighbors. There's no gradient descent, no training process. So there's no parameters to be learned. Therefore, it's non-parametric. There's no cost in the learning process. So the learning is really efficient because the learning is just collect the data and then you're done learning. There's no learning involved in k nearest neighbors. It's really intuitive, etc. But disadvantages, I don't think I can, but I will post these after. And yeah, for today, I'll just read it out loud. So disadvantages of k nearest neighbors, it could be very expensive computation because you need to loop through all of the data points and calculate the distance from your input data point to all those other data points. And therefore, it's O of your data set. Pretty inefficient versus, say, logistic regression, where you just plug in your input data into an equation, really efficient. You're just calculating a formula versus looping through every data point. So these are the types of things to think about. Actually, I don't want to go through all of these since you can't see it, but go look at this table and kind of understand it. If there's any data, there's any point here where you're a little confused about why it is, maybe bring it to the beginning of next class and we could address it before the exam is released, which will be right after next class. Here's another version of those tables. So I'll post this right after class. Take a look at these slides, look at other resources online. And if you're ever being like, well, why is k nearest neighbors actually faster than logistic regression for training? I don't understand that. Then come to class with that question. Yes.
Is this something like what we're gonna do for the exam, like compare the model and say why one is better than the other?
Kind of. I'll give several example questions today, so you'll get a feel for what types of questions there are. So looking at those tables is a good way to study, thinking through what's the difference between these models. Another good way to study is just to look at the scikit-learn documentation and ask yourself if you understand what each of the hyperparameters that we've talked about in class are doing. And we didn't talk about all the hyperparameters in class, but if it's a hyperparameter that we talked about in class, understand why would I either use this hyperparameter or not? And what's the trade-off between different values of this hyperparameter? Things like that. So for example, here's the beginning of the documentation for a decision tree classifier. And we see that the first hyperparameter is the splitting criteria, Gini, entropy, log loss. So make sure you understand that. The splitting strategy used, are you gonna split with the best split, or are you gonna choose a random split, the best random split?
What do you mean by, what is the best split?
Choose the best split. I think like you split based on the criteria and you choose, look at several ways to split your data and choose the one that's the best.
Oh,
Um,
what does that mean then?
so
Sorry.
so when you're doing a decision tree, like in your homework, you're splitting the data on different on a variable,
Oh,
right?
okay, so it'll choose whatever variable has the biggest discrepancy.
Yes.
I see.
Max depth. So you can, instead of building your decision tree out to the bottom, you can say, I'm not going to have my decision tree have more than 5 layers, things like that. I put in a bunch of these for a lot of different models. So do this for all the models we learned in class, and I think you'll be in good shape. Again, this exam is open notes, open everything except open person. So you can write these out for yourself too, and just have it as reference if you want to do that. And yeah, understand trade-offs between not just within a model, so within the hyperparameters you can choose, but between models as well. So what's the learning speed or training speed and memory cost versus the prediction speed and memory cost? Types of decision boundaries that could be learned. Is it linear? Can it learn nonlinear boundaries? The types of predictions it can make, classification and regression versus regression. Can it only do binary? Can it do multi-class? Is it for supervised or unsupervised, etc.? And okay, so we're about to get into sample questions. I just want to leave you with a note that all these models are engineered by people and they're not laws of nature. So it's not like logistic regression was something that was discovered. It was something that was created by people. And that's a general theme of all of machine learning, is that all of machine learning is invented by people. And so you can change any of these models you want and run your machine learning model in that way. And I actually recommend that you do that. But before you do that, you need to understand the rules before you break them. Or in other words, if you're going to make a change to a model, or ask yourself, if I did it this way instead of the way that you're teaching it to me, what would be the implications of that change? And if it's a fine implication, then you should do it. What I'm teaching you is just the common starting place that are like common models that people tend to use. Okay, so let's go into some example questions. Okay, so first question, and for all of these, we'll do votes. So true or false? Training a k-nearest neighbors classifier takes more computational time than applying it. Who thinks? Let me give you a few seconds to think about it. Who thinks true? Who thinks false? Okay, let's get a hand for true. Can someone who said true explain why true?
So I thought it was true because it's like you were saying, is you have to calculate the actual distance between each point, which when you're dealing with many points will take time. So the actual like computation is quick, but like the application of it would be really simple.
Okay, and how about for false?
I think, you don't actually train a k-nearest neighbors classifier, you just apply it.
Right.
Uh,
So the answer I had was false, because there's no training involved, so it can't take too much computational time, because all you do in k-nearest neighbors is test. You have your data already. There's no training in the first place, and you just look at all the other data points. Okay, let's keep going. So true or false? The more training examples, the more accurate the prediction of a k-nearest neighbors model. Give you some time to think about it. Okay, who thinks true? Who thinks false? Okay. Wow, okay, this might be a harder example. So I put true because and if you have more examples, you're gonna have when you look at your nearest neighbors, you're probably gonna be more accurate because there's more neighbors. Yes, Chris.
Could you maybe say then examples instead of training examples?
Yeah.
Because
So
here,
there's no training involved.
yeah, we don't train. we don't
That's a
like-
great
like-
point. Yes. Yes, Chris, that's what Christoph said, just for people online, that technically you don't even train K nearest neighbor, so it's training examples the right. Yes, good. That's a great point. Here I meant training examples as in what goes into X train and Y train. Because you still call it X train and Y train and scikit-learn. But yes, technically the training is like return true, and that's the whole training process. Also on this exam, if there is something ambiguous like this, like we can drop that question. So if there's something where like you come to me and it's like, well, I put this, but I thought it was this, and your reasoning was good, could totally drop it. Yes.
Examples we have is from our class.
Mhm.
It may be like everything wrong.
So you're saying, so the point was there might be a class imbalance. We might have 99% one class, 1% another class. And how would that affect this question?
So like, which one is like nearest neighbor, will that affect the prediction?
Would a class imbalance affect the prediction? It could, yeah, but if you have more examples, in general, you might expect it to do a little bit better because there's more examples. So if there's 99% in one, if you're looking at the 5 nearest neighbors, even though there's a higher probability if you chose random neighbors, that it'll be not the majority class. Since you're doing the nearest neighbors, it's likely that the neighbors that are closer are in the same class. I'm gonna skip this one. So okay, true or false? K nearest neighbors is sensitive to outliers. Think about it a little. Okay. Outliers can affect the results.
Oh,
Okay, true. Hand raise. False. Okay. For those who said true, someone from the true camp. Yes. Mm-hmm. And why, what about for someone who said false?
You have an outlier that should be pretty, at least visually, far away from the rest of the data you have. So the only time it should affect it is if your example is already in the outskirts of your data. But in most general cases, if you pick an example in your data set, there should be a pair or multitude of points closer than the outlier.
Yeah. I agree with both of your answers. So this is this will be an interesting exam. So if you make a good, so my answer was true because if you're by a if you have an outlier, it's going to affect your prediction severely if you're near the outskirts. But yes, I do also agree that in the general case, the outlier is not going to affect things, but it does. I guess maybe it's the wording. It's is sensitive to outliers. Yes.
does that also include the number, like, isn't it also based on the number of sample points that we have? So the fewer the sample points, the more sensitive it would be to outliers?
The more data points it has, the more sensitive it
No,
is.
the fewer data
Oh,
points.
yes. Yeah, exactly.
But
Yeah.
I would say
Okay,
is
there, sorry.
the higher the K, the less sensitive it's gonna be to outliers.
Yeah, I'd agree with that statement. Yes.
I don't understand. I thought you said that it was multiple choice, so how are we gonna argue?
No, I'm saying like if you don't like your, like you get it graded and then everyone in the class is like, well, this question was ambiguous, then we can drop it or give everyone the credit for that question.
Okay.
Yeah, you can't do it during the exam. So don't email me during the exam. It's a timed exam. But after the exam, don't be like, this is your final score. It's like, it's negotiable. Yes.
When you write depends on K and data points with the count,
If it depends.
because it's not true or false, so it's kind of both, like
Yeah.
depending on these parameters.
Like if after the exam you send me that in an email, I'll be okay. You get that point back. But there's not a text box to explain yourself because it's a
So it's really just like moving forward.
it's really just multiple choice. But if it is something where you actually, it could be either way and you have a good argument, like I'm not going to be a stickler, like, oh, I happen to put this one, but like if you understand the material, you should get the point.
I have a general question about the exam structure. Just because I know it's time from when we started, will we have an opportunity after the exam to still go back and like read the questions? Because just in the case where, say we do a question where it's either something like this where it's ambiguous or we're conceptually stuck, I don't want to lose time and like miss out filling out other questions because I was worried I wouldn't be able to go back and like at least think about it and then be able to make my explanation for it.
Yeah. So you don't have to make an exam explanation on the exam, and there's not even a text box to do that. But with regard to your question, I don't know, does the La Lima interface and other exams that you've taken allow you to do that? Go back and forth between questions. I have to do that. Okay, so I'll make sure to set that up. Okay, so the default is you can't go back, but I can change it to allow you to go back. Okay, yeah, I think you should, I'll remind me if by next class and I'll confirm if I've done that or not. Or let me just write a note here. All right, allow students. Remind me to look behind me, so. To skip.
I'm not sure because I don't know if I don't remember if I allowed to talk to Lima before, but I think like it would be helpful if there was something which can force us to answer all questions. So that when we skip stuff, we don't forget. I think the default is that you have to attempt everything, but I'm not sure. I think there was one case of an undergrad homework where someone skipped the question, they did not give a notification.
Okay, yeah, let me make sure. There.
Yeah, but someone might submit it that was never. So when we submitted, like sometimes it tells you that we haven't.
So, okay. Good. Okay. Here's hopefully most of it will be less ambiguous. So like this question. I kind of started off with very ambiguous ones. So I apologize. Don't be scared though. It's not like that. So which of these models separate the following data? So we have red circles and triangles that are gray. There's no debating this one. It's just either it can or it not, or it doesn't. So raise your hand if you think logistic regression can separate these data. Raise your hand if not. Okay, so the majority is not in. Remember from class, logistic regression could only learn linearly separating boundaries. That's all over the place in the notes. And there's no line that can separate these data. So logistic regression can't learn this decision boundary. What about a hard margin support vector machine that doesn't use a kernel to increase, or doesn't increase the dimensionality of the data in any way, just a plain hard margin SVM? Who thinks, raise your hand if that can separate these data? Raise your hand if it can't. Okay, majority said can't. Good, because it's just learning linearly separating boundaries by definition. What about a support vector machine with a polynomial kernel like the one we learned about in class? Raise your hand if it can separate that. Okay, raise your hand if not. Okay, good. What about a decision tree? Raise your hand if you think it can. Raise your hand if you think it can't. Okay, so mostly said it can, but there are a couple it can't. So decision trees, if you recall, are recall from in class that they yeah, let's look at two-dimensional data, x1, x2. It doesn't even matter how the data are separated, but let's say you split on x1. So is x1 less than a certain value? If yes, go this way. If no, go that way. That's splitting the data like that. And then you might ask from there, is x2 above this certain threshold? Yes, or is it above this threshold? Yes or no? If yes, go this way. If no, go that way. That can split the data like that. And so each time you split the tree, you're partitioning the space, and you could potentially keep on splitting and get any separating boundary that you want. So that's why, yes, decision trees can learn this data, and it could, in theory, learn any data. It might overfit severely to the training data set, but it will do really well on the training data set specifically. What about 3 nearest neighbors using the distance formula as the way of calculating the distance? Who thinks yes? Who thinks no? Okay, good. Okay, so this is maybe more in line with the difficulty. Yes.
Yeah, SVM is with polynomial kernel.
So SVM with the polynomial kernel is where you project the data into a high dimensional space.
You could do that with this one, right?
Yeah, you could project any data. So SVMs can, in theory, learn any decision boundary if you give it a powerful enough kernel.
So why is it not suitable?
It is.
Oh,
The SVM with the polynomial kernel is. Yeah, the first one's not, because there's no kernel. It's just
okay, sorry.
no, sorry, this one's not a multiple choice. This one is each one either can or can't. So sorry. Yeah, it's not one or the other. Sorry, you don't have a question like that on the exam, by the way. There's no select all that apply, because it's always like, oh, what if I just miss one, then I miss, yeah. So none of that is just for today for reviewing the concepts, but there will be true and false and multiple choice. Yes.
So SVM with the polynomial kernel, you project it into a higher dimension.
Yeah.
So like, you can imagine like that in a plane, and those circles are higher up and the triangles are lower.
Exactly.
Things like that cut off in between.
Yes, exactly. And you could imagine many dimensions beyond a plane. But yeah, exactly that.
The fact is that the faster one between the two,
For training or for testing?
the training.
For training, probably nearest neighbors, because
Oh, no, between SVM.
probably decision tree, because there's no gradient descent type of thing involved. It's just split the data, you calculate the metrics, and you keep doing that till you're done. But it could depend on the size of the data set and the max depth and things like that. So it kind of partially depends on the hyperparameters, but in general, decision tree will be faster to train. SVM will be faster to predict, because it's just an equation and you plug it in and see what the value is. Okay, here's a question from actual final exam from some other school. So suppose we have a regularized linear regression model, and then the equation for linear regression. What is the effect of increasing lambda on bias and variance? Yes.
And what the on the subscript? What is the 1 on the 2?
So the subscript is telling you whether it's a L1 or L2 norm.
Oh, okay. And when it's above, it's a square.
It's a square. Yeah.
Okay.
Yeah, these are, I haven't used that notation too much in class, but in like math world, that's the notation. I won't make you know that notation for this exam. But apparently this class makes you need to know that notation. Okay, so quick reminder, because I know you probably don't remember it off the top of your head, but remember in your notes where to look when you're taking the exam. So bias and variance, that's kind of the key to this question. What is bias and variance? So can someone remind me, what is bias? When a model is biased, what does that mean? In terms of overfitting and underfitting, which is the key.
It's overfitting.
Overfitting. What about variance? So yeah, these are okay. So this is kind of a this is terminology, but a way that I like. It's commonly used terminology, and it's in your notes, so it's useful to know, and you could reference it in your notes when you're taking the exam. But the way I like to remember it is that bias is saying that your model has high bias towards what the decision functions should be in advance, and therefore it's underfitting because it's biased towards a certain decision function, versus variance is overfitting. You could think of it as the model has a lot of variance, has a crazy polynomial, it's varied all over the place, and therefore it's overfitting to the data. So bias is just synonymous with underfitting. Variance is synonymous with overfitting. And just good to know that. I know it's kind of terminology, but in tech interviews, they like asking that terminology. So good to know. So given that increasing bias means increasing underfitting and increasing variance means increasing overfitting, the question here is, what's the effect of increasing lambda, the regularization parameter, on this? Yes.
I would say it increases underfitting and decreases overfitting.
Yeah, increases underfitting, say that again?
It increases underfitting and decreases overfitting.
Mm-hmm. Yeah, so it decreases overfitting, and that's kind of the whole purpose of regularization, is to decrease overfitting. So therefore, what's the answer to this question? Shout it out. Okay, yeah. So B, yeah, exactly, because it's increasing bias means it's increasing the underfitting. It's preventing the model from fitting to like a complex function. It's decreasing the variance, decreasing the propensity of the model to overfit. And remember when we had this type of thing in the notes back in the day, overfitting, high variance, the model's highly variant. Underfitting, the model didn't learn something complex enough. It has a high bias towards, in this case, learning a line when it should have the power to learn a parabola. And a good balance would be low on both, low bias, low variance. So that's what you want. So again, bias and variance, just synonyms for underfitting, overfitting. And they might show up as either way on the exam. Okay. True or false? Okay, I don't want to ask another k-nearest neighbors question. So, okay, true or false? A tree with depth of 3 has higher variance as defined just now than a tree with depth of 1. So think about it a little bit. You'll have like a minute to think about each of these questions on average. So I'm gonna give y'all time, and just to see when you have time how y'all do. Okay, who thinks true? Okay, who thinks false? Okay, very good. By far, most people said true, and that's because if you have a depth of 3, you have more propensity to overfit. You're considering more variables. You're learning a more powerful decision function than if you only have a depth of 1. You can only split the data once, and you can't really overfit as much with that. So majority got that. Okay, what about this one? A tree with depth of 3 has higher bias than a tree of depth of 1. Who thinks true? Who thinks false? Okay, yeah, it's just the opposite. Okay, a tree with depth of 3 never has higher training error, which is error on the training data set, not the test data set, the training data set, than a tree with depth of 1. Think about it a little bit. Basically saying depth of 3, it's never going to have more training error. It might have equivalent training error, but never more training error than a tree with a depth of 1. Yes or no? And that's just on the training set. Again, not on different test data, on your training data. Okay, who thinks true? Who thinks false? Okay, so the answer is true. I think, so the reason is that if you're training a model, going back to this picture, if you have a depth of 3, you're going to split your data more, and therefore you're going to do a better job at splitting your data, and therefore you're going to have less error than a depth of 1, where you're only splitting your data once, and so you're going to probably have lower training error, and you're definitely never going to have, sorry, with a depth of 1, you're going to have higher training error because you're only splitting once on the training set.
Error on the test data set, that would be false, right? Because just having higher depth in the.
Yeah, if it was, so the question was on, would this be the same for test data? And that's actually the next question. So, okay, so the same question, but on test data, what do we think? So everything's the same except test error. Who thinks true? Who thinks false? Okay, yeah, very good. So,
Parentheses error, right?
oh, yes, yeah. Error on the test set. Yes, yeah, so that should say test set. But if I make a typo on the exam, that's good cause to give you that point. Like, well, I technically thought you meant training set. Okay. Let's see. Decision trees with depth 1 will always give a linear decision boundary. True or false? So who thinks true? Who thinks false? Oh, okay, cool. And it just comes back to this question or this picture. If you have a depth of 1, you just do 1 split. That's a linear separating boundary. Yes.
When would it not be a linear? Isn't it just different multiple like linear combinations sort of? Or like isn't it still always linear?
No, because like in this example, you might have, so the question was, isn't it always linear even when you have lots of separating, because isn't a bunch of lines equivalent to just linear? Let's say which I'm just gonna shade it in. Okay, I don't know. So like this, for example, I have different colors. Okay, no. This separating boundary, oh, I got it wrong. The separating boundary that the equation for this shape is not linear. That's separating the blue from the red. Like it's like the more lines you have, you're approximating a more complex thing. You're creating something more complex. So it's only linear when you have a stump or just one, you split it like that or split it like that. And then it's literally a linear decision boundary because you're saying, is it to the left or right or up or down?
It's only like the equation for a line to an equation.
Yeah. Like even with 2 splits, you can have a sigmoid looking decision boundary all of a sudden with a depth of 2.
Wait, it's not that 2 would require a quadratic decision boundary?
It depends. You could have different types of decision boundaries with depths too,
Okay,
depending on how you split.
I thought it would always be quadratic, because
That's something good to think about. But you could think about how that would not necessarily be a quadratic
Would it
boundary.
always be a two-dimensional, bit boundary?
In two,
Depth is two?
so if depth is 2, is it a 2D boundary? I think so. Good question. It depends on the dimensionality of your data, though.
Because like one split could cut the plane right with the into the plane, so that would be a like three-dimensional split.
Yeah.
Just split that to one.
So you're saying with a depth of 1 and how the dimensionality of data being,
Like three,
okay, so 3-dimensional data, depth of 1.
You're like cutting the plane right. from the-
Yeah, so you could think of it like that. But you could also think of it as you're split, yeah, the split is a plane. Yes, exactly. Yeah, the split is a n-1 dimensional hyperplane of the data using the SVM terminology.
So then the decision boundary is like the aggregate partition that separates everything, or like the classes we're trying to identify or whatever from each other, not necessarily just each decision.
Yes, exactly. So this is training data, and then you get test data, and you might have it be over here. Here, like what is this data point that's here? And well, because it's in the dot side of the decision boundary, we classify it as a dot, even though that data point wasn't in the training data.
So the question, like, it's very prone to overfitting, right? Because like the higher depth you have, you could give it like very tight boundaries for each like test point, right, or each training point.
Yeah, that's a great point. So the point was that if you have a really high depth of your decision tree, it has the capability to overfit. And yeah, it exactly does. And that's often why we use that max depth hyperparameter, because we don't want it to overfit too much. But yeah, great observation. Oh yeah, I guess I had a picture already here. I forgot about that. That would have been easier than the whole board thing. Okay, true or false, logistic regression will always give a linear decision boundary. Who thinks true? Who thinks false? Okay, good. I think we talked about that ad nauseum. That's literally from the notes.
Sorry, it's a quick question. What would it be? What is the model called where you could run a polynomial line that splits between two?
You could call it, well, it depends. There's different ways. So you could actually call that logistic regression if you do feature engineering and you make your features a combination of X1 and X2. So there's a way to make logistic regression learn nonlinear decision, but as we defined it in class, it could only learn. Yeah. So if you know other like special cases beyond this class, it's only the exam is only going to be stuff we talked about in this class.
So logistic regression means that like n is supposed to be line that separates.
Yeah. But you could, of course, modify logistic regression easily to learn nonlinear. And we actually showed that in class too.
But
Yeah. Okay, so this one, actually, I'll just let you read it. This is from a actual final exam from a machine learning class at a different school.
Can you see some of the examples like even on the same data set? Like, or is it from the different data sets? No, it's on the same data set.
One data set with 100 data points in it.
Oh, okay.
Okay, who thinks the answer is A? Okay, I'll just stop there because that is the right answer. The reason is because, okay, we have 100 data points and we want to do 10-fold cross validation, pretty similar to the homework. And so for N1, we want to compute the error 10 times. We're splitting it into 10. So that already gives us A, C, and D as possible answers. To compute each error, we need to build a model with a data set of size N2. Well, if you split 100 and you use 10 for test, then 90 for train, and that's how you get N2 and N3. And usually you want much more for train than in test, like in the homework and like in class. Cool. This is just another question from a previous exam from some other school. In each round of add a boost, and remember you'll have your notes, the misclassification penalty for a particular training observation is increased going from round T to round T plus 1 if the observation was, that's one of the random forest like approaches we learned in the ensemble learning class. So this one is just straight from the definition of add a boost. Does anyone happen to have their notes handy and know the answer? What was it? Okay, so we got an A and YA.
I believe that the other guys have to work with it. But so I'm guessing like it's either A or B.
Cool.
of the two.
Okay. Yeah, I mean, this is open Google, by the way. So like you could do that and it's not cheating. Because like in the real world, like when you code, it's open Google too, right? So yeah, why would you make it not real world like? It's not like you don't have Google when you're doing machine learning. Okay, so yeah, the answer is A. Okay, true or false? An important advantage of support vector machines is that they can directly implement classifiers with a large number of classes. Who thinks true? Who thinks false? So, okay, not too many. Well, this one is false just because by definition, it's separating into binary. And we didn't talk about this in class, but if you wanted to make SVM multi-class, you can create several independent binary classifiers using SVM, but that's certainly not an advantage because inherent to the method, there's no binary. I mean, it's only binary in terms of the method we learned. Okay, true or false, the ID3 decision tree learning algorithm can only work for binary classification problems. That's the decision tree learning algorithm that you use in your homework and then we went over in class with the example and we labeled it ID3 there. So who thinks true? It could only work for binary. Who thinks false? It could also work for more than binary. Okay, so the answer is false because you can predict whatever you want at each node. It doesn't have to be one thing or the other. You can predict anything kind of by definition of the model. Okay, true or false, an advantage of using decision trees for machine learning is that the classifiers produced can be easily implemented with rules. Thinks true. Thinks false. Okay, so yeah, by the definition of a decision tree, it's rules that you follow to go down the tree. So true. We already talked about this, but in theory, a decision tree with n Boolean variables can represent any Boolean function over n variables. Who thinks true? Who thinks false? Okay, so the answer is true exactly for this. If you keep splitting, you can get any function that you want. Here's another picture of that. Okay, in model-based learning methods, an iterative process that takes place on the ML models that are built based on various model parameters is called blank. Just shout this one out. Hyperparameters, yes, good. Okay, which of the following models is capable of learning a nonlinear decision boundary? Everyone see these? Who thinks A? Who thinks B? Who thinks C? Who thinks D? Okay, so the answer is B. And look back at the logistic regression notes, and we did a very similar example to this. But basically, there's a nonlinear function inside the sigmoid. And so just off of that, it's going to be nonlinear. But we go into more details in the notes of showing exactly what kind of decision boundary that can learn. Which of the following models is not optimized with a loss function? So who thinks logistic regression? Who thinks linear regression? Who thinks naive Bayes? Okay. There are a lot of questions at that level on the exam, by the way. Which evaluation metric below performs poorly with an imbalanced data set? Who thinks negative predictive value? Who thinks positive predictive value? Who thinks accuracy? Okay, and we'll stop there. Again, the whole reason we motivated all these other metrics was because accuracy doesn't perform well with imbalanced data sets. So that's the whole reason we look at all these other ones. And definitely reference this, maybe even have this page open, Wikipedia page of precision and recall, which has this beautiful figure with the definition and has all the definitions for you. Or the notes also have all that. Okay, so simpler models are only preferred over more complex models when there are limited computational resources. Think about it. So we'd only want to use a simpler model when a complex model is too expensive to use on a computer. Who thinks true? Who thinks false? Okay, so the answer is false, because the overfitting, underfitting thing we've been talking about a lot. Just because you can do something doesn't mean you should in life. Yes.
You could just really tune in with hyperparameters to a point where it's not really overfitting anymore, and you still like go for the more complex model, but you like, I don't know, play a lot with hyperparameters.
Good point. So you're saying, well, what if you have a complex model, but let's say you do regularization and you play around with the regularization strength as a hyperparameter, and therefore you give the more complex model the propensity to become a simpler model. Yeah, I mean, technically that's a good point. But at this point, I guess the point was that it becomes a simpler model and therefore you prefer. But yes, that's a good point. Yeah.
So basically, like, you wouldn't use a very complex model when you know that there's like a linear sitting out there.
Yeah, and or if you have because if you use a really complex model, it can potentially learn any decision boundary. So not just nonlinear, but any decision boundary. And if your data is really noisy, maybe you don't want that. Maybe it's not even, is it linear or not? Is it noisy data or not noisy data? Is it, things like that. Is it a small data set and really complex decision boundary? Then it's definitely going to overfit, and don't want to use a big model in that case. Okay, almost done. Which of the gradient descent methods below is fastest during each iteration? Okay, who thinks batch gradient descent? Who thinks mini batch gradient descent? Who thinks stochastic gradient descent? Okay, cool. Yeah, stochastic gradient descent. Because remember, stochastic gradient descent just uses one training example per iteration. So it's going to be faster because it just uses one data point. Okay, if the loss function is convex, then gradient descent will eventually converge towards a global blank. Maximum, raise your hand. Minimum, raise your hand. Okay, so the answer is minimum because it's convex. And so we want to get to the minimum loss function. And yeah, again, it's all in your notes. If you're like, which one's concave, which one's convex, just you'll have your notes. And so it's not like you have to memorize this stuff. Okay, true or false, gradient descent only works for two-dimensional input data, like we showed in class. Who thinks true? Who thinks false? Yep, gradient descent works for neural nets and for any type of complex model. True or false, gradient descent, as we described in class, will work with a non-differentiable loss function. Who thinks true? Who thinks false? Okay, so most said false, and that's because by the definition of gradient descent, we're differentiating the loss function, and therefore
What is a non-differentiable loss function?
a function where the derivative is not defined. And there,
Doesn't every function have a derivative?
nope, there's many functions that don't have derivatives that are defined. There's functions where you can approximate a derivative, and there are modifications to, you don't need to know this for the exam, but there are modifications to gradient descent where you can define a loss function that's not purely differentiable. And actually SVMs are optimized in that way. The hinge loss is not differentiable purely. And so you can modify gradient descent to work in that case, but gradient descent, as we discussed in class, and kind of the basic unmodified gradient descent needs a differentiable loss function. And again, if you know stuff beyond this class, this exam is just asking for what we've learned in class. So that's the last question. Who thinks this is too easy? Given that it's open notes, 75 minutes, 75 questions or something. Who thinks it's just right? Okay, who thinks it's too hard? Okay, so like, we'll see what happens, but we can,
Yeah, I'll say it was good, but it's just easy.
okay.
Some bustling knowledge.
Yeah. So as you can see, you're not gonna have to do any calculations. You might have to calculate fractions, and you might have to calculate like precision and recall type of stuff.
Open calculator.
Open everything, yeah. Okay, thanks.